collects more light, and that allows you to look fainter and deeper into space. So that's the most important parameter, is the area of the mirror and the collecting area, okay? And so that's why we need bigger and bigger telescopes. The larger, we have more area, we can collect more photons and look deeper into space. So this is an example. On the left, you have a galaxy. On the right, you have the same galaxy, but observed with a larger telescope. And so you can see that when you observe it with a larger telescope, you collect more light, you're able to see details that you didn't see before, right? All the fainter emission coming from the lower left side of the galaxy is not visible until you take a deeper exposure. And that's how you see that all that details, all that structure coming from the galaxy. So all this emission is there. It's just that we can't see it unless we go deep enough. And this is not even the deepest you can go, right? If you take the same integration or 10 times the integration time, you will be able to see even fainter and fainter structure from this particular galaxy, for example. Okay, so where are these telescopes? All these telescopes are the ones that I work on, and some of them are at the summit of Hawaii, the summit of the Mauna Kea volcano in Hawaii, which is about 4,000 meter altitude in the summit above sea level. And you will see this picture of the summit. And there are close to 8 telescopes, right? And many of them are 8-meter class. Keck telescopes are actually 10-meter diameter. And they are built on top of the summit of Mauna Kea, because the higher you build your telescopes, then you are above a larger amount of the atmosphere. That's why you want to build them at the highest altitude in order to avoid all the atmosphere that you can, right? And so now this leads me to the concept of the resolution of the telescopes. So what is the resolution? It's essentially an angle that we measure, and it's basically measuring what is the minimum distance at which we can resolve 2 objects, right? 2 point sources. So a better resolution means that we can resolve objects, point sources that are closer together. And you have to think that astronomy detectors collect the data in pixels. So that's what that diagram is showing on the lower right. That's essentially a matrix of pixels, and each pixel has a number associated with it, right? An amount of counts or amount of photons. And so because the way that we collect data is discrete, right? It has a physical size, then the size of the pixels will determine the resolution that we obtain from the astronomical images. So that example, right, where you have several numbers, zeros and ones and so on, translates to the same diagram on the right, where you see that 2 blobs, 2 stars, but they are pixelized, of course, because the image is made out of pixels. So this is what affects the resolution that we end up having when we take images. So for example, say we want to resolve individual stars in the galaxy shown in the top diagram, right? So that's the same galaxy taken at 4 different levels or seen at 4 different levels of resolution. So it is very blurry at first, and when we increase the resolution, you see that you're able to distinguish individual stars in the galaxy, right? That's what high resolution does. The same at the bottom, that diagram is showing how when you increase the resolution, what seems just to be a blob, or it could even be looked at as a single star, it's actually a collection of many stars. In this case, that's a cluster, a stellar cluster, which is the object that I'm interested on. So that's what high resolution allows us to do. Another example, just to show it on a graph, right? That's how you basically define whether 2 objects are resolved or not. right? At the further right, you have both objects close together you cannot resolve. And when you move to the left, you are starting to resolve them, and then until you eventually completely resolve. And when you say you resolve them, that means that you're able to measure each profile of luminosity individually for each point source. So the way we can parameterize the resolution in a more technical way is through the diffraction limit of the telescopes. The diffraction limit is a function of the wavelength of the light that we're observing, and also a function of the diameter of your telescopes, right? So keep in mind that it's directly proportional to lambda, which is the wavelength, and inversely proportional to the diameter. So that means that higher wavelength, right? Higher wavelength will give you a higher diffraction limit, and that means low resolution. So when you're observing high wavelength radiation, like radio wavelength, for example, that means your resolution is going to be very, very bad. So when you do radio astronomy, which essentially is observing radio wavelengths, you have to compensate. And how do you compensate is by building very big telescopes, by making the diameter very large, so that it can compensate for the fact that lambda is also very large. So when you do that, you end up with huge telescopes, and that's the way radio telescopes look like. On the top left, that's the Green Bank telescope in the US, and this is a dish that I think it's 100 meter in diameter. So it's a huge telescope. We have nothing like that in the optical. We plan to, but not for many decades. But in radio, you can do it. You have 100 meter telescopes like that, Green Bank, and Arecibo at the bottom right. That's actually 300 meter diameter. Unfortunately, Arecibo was partially collapsed in year 2020, so we can no longer use that telescope. So here an example of what happens when you combine optical observation and radio observation, just to give you an example of the different resolutions. So the colors are coming from actual optical observation. I think in this case it's Hubble Space Telescope. And the contours that you see on top are just the emission coming from a radio telescope. And immediately you see, if you were to just take the contours and forget about the optical, that's all the information you have, right? You know that there is some kind of a blob at the top left, and then you have some fuzzy structure in the center. You cannot resolve any detail or anything. That's what radio looks like. Most of the time, radio telescopes just give you a broad, a very fuzzy image of the objects. So that's, again, limited by the resolution that we can obtain at each regime, at radio or optical, and so on. Another aspect of observations is the limiting, the way that the atmosphere limits the resolution itself. So it's not only the type of light, it's not only whether it's radio light or optical light, it's also the atmosphere above the telescope that will limit the kind of observations that you can do. And that's one way to parameterize that is through the seeing. So let me just play this video quickly. So the fluctuations that you're seeing here, this is an image of the moon, right? Taken with just probably a normal sized telescope. The fluctuations is just due to the fluctuations in the atmospheric layers above the telescope, right? So oh, sorry. So that's why it looks like it's moving around. That's just the atmosphere. And the seeing is essentially the result of this, right? When you, instead of having the moon, if you had a star in there, the seeing makes the star to move around, just in the same way that the moon, this image of the moon, is moving around. That's what the seeing does. So that's a huge problem, and there are ways to overcome it, and I will talk about that in later slides. So how does the atmosphere affect the observations? Well, there are different windows, so to speak, in which we can observe. At the top, you have a graph showing the opacity, which means how transparent the sky is. So at the left, you have UV light, gamma, X-ray, and all of that. And at the further right, you have long wavelengths, so radio waves. And around the middle, you have the optical window, right? Which is, you see those colors. And right to the right of the optical, you have the near infrared window, which is, roughly between 1 micrometer and between maybe 5 micrometers. So that's the window of near infrared observations. You have also far infrared and radio waves as you go further right. So the plot is showing that at different wavelengths, you have different opacity of the atmosphere. So the atmosphere doesn't let any kind of light to penetrate to the Earth. It's only certain wavelengths that can penetrate fully to the Earth. So there's no point of building, X-ray telescopes in the ground, because you're not going to get any radiation of X-ray, barely any radiation, right? Because the atmosphere is absorbing most of it. The atmosphere is very opaque at that wavelength range. So this is what determines where you can do ground-based astronomy, is whether or not the atmosphere is opaque at that regime. I'm now drawing a circle where the near infrared window is. So that's essentially roughly where the location of the near infrared window is. At the near infrared wavelengths, you have different windows, right? That's a good way to put it. And we name each of these windows with a different letter, right? J, H, K, L, and M, for example. And each of these letters will define a certain narrow band that we can do observations. And this is actually what defines the kinds of filters that we build to do observations. So you will put a filter on front of your telescope, on front of your detector, I'm sorry. And that filter will filter out any light that is not within that range of radiation, right? So if you want to do an observation in the K-band, we put the K-band filter, of course, and then we take all that radiation that, as you see, is maximized, is optimized for these windows of high transmission. If you have low transmission, when the curve is very low, there's no point of observing at that wavelength because the transmission is low, therefore you cannot get almost any light anyways. So this is the reason why the filters are made the way they are, because they are responding to the way that the atmosphere is interacting with the light, okay? So there's background sources, of course. So it's not only the universe that it's emitting, it's also the atmosphere is emitting as well. The atmosphere is very bright actually in the near infrared. So here is a plot of the amount of photons, the amount of emission that the atmosphere radiates as a function of wavelength. And this is also, again, still in the near infrared regime. And you see that atmosphere is emitting a lot of light, and most of it is coming from OH lines, and we call this the air glow. It's just the emissivity of the air of the atmosphere. So the dark sky is never fully dark. If you're observing from the ground, it will never be fully dark because the atmosphere itself is emitting very high emission, especially in the near infrared. And to make matters even worse, the air glow is very bright, so you need short integration times, otherwise you saturate your detector. But not only that, it actually varies rapidly as a function of time. So now you have a plot showing the air glow emission, right? The strength of the emission as a function of time, measured in Hawaii in this case. So you see that it fluctuates. It goes up and down and up and down. So you have to calibrate for this effect throughout the night when you're taking observations, right? It doesn't help if you measure this effect at the beginning, because by the end of the night, it's going to be completely different. You have to be taking care of this throughout the night. And this is something that we do constantly when we observe in the near infrared. So just to summarize, I was talking about, right, the background sources, right, that we have to deal with when we make observations in the near infrared. You have the atmosphere, as I mentioned. The atmosphere itself has a temperature. So because of thermal emission, the atmosphere will radiate only because the atmosphere is higher than zero. Anything that has a temperature higher than zero, than absolute zero, will emit some near infrared radiation. You also have the OH emission, right? The air glow that I was just describing. On top of that, we also have the zodiacal light, which is just particles that are floating around in space. And these particles get charged and also emit kind of radiation. So this is also another background source. And of course, the telescope itself has a temperature also. Telescopes are not fully 0 degrees, so they also emit and the thermal, they also do thermal radiation. Everything in the telescope, the mount, the optics, absolutely every part of the telescope is also emitting. So there's background sources, there's background contaminations everywhere in the infrared. That's what one of the reasons it makes it so complex. So now let me just describe a little bit about the Gemini Observatory. As it was described at the beginning, I was a science fellow at Gemini Observatory for a number of years until recently. And the Gemini Observatory is a collection of 2 telescopes, actually. So this is going to show the location of the telescope in Hawaii, right, is right there. And there's a similar telescope in Chile, actually. So this is the archipelago of Hawaii. The big island is, of course, the bigger island. And the red dot is Hilo, which is where the office, the control room of Gemini Observatory is, in the town of Hilo, which is where I live. Again, that's the red showing where Hilo, well, actually, that's not Hilo, that's the volcano, I'm sorry. That's showing the lava flow of the Kilauea volcano. That's the office of Gemini Observatory, where the control room is. And this animation will show both telescopes and their location. You have one in the south in Chile, and you have Gemini North in Hawaii. So when you combine them, you get the full sky, right? And that's the reason why Gemini decided to build 2 telescopes, one for the south hemisphere and one for the north hemisphere, because that way you are almost covering the entire sky, right? So it's really great that they get to do that. So between Gemini North and Gemini South, there are many different types of instruments. Each instrument is optimized for a different type of observation, different wavelength, and the color of that you see here, whether green or red, is showing whether the instrument is optimized for the optical or for the infrared. And some instruments are using a technology known as adaptive optics, which I will explain briefly later. And so I'm just gonna now stop a bit more. Later, I will explain a bit more about the GSAOI instruments and the GEMS instruments, which is the AO instrument at Gemini South. And again, just to show you the different, how different each instrument is at Gemini, each instrument will be optimized for a different level of field of view, which essentially is how far you can look, or the level of zoom, to put it in simple terms, is the zoom of the observation, and also at different wavelengths, right? So each instrument is optimized for a different regime, for different kinds of observations. Now, again, let me go back to the seeing, right, that we mentioned earlier, right? We saw this animation, we saw how seeing is essentially the atmosphere that is having turbulence, right? Is the turbulence of the atmosphere above the telescope, right? That's what seeing is. So how do we deal with that? When you have a point source, like in this diagram, this point source is emitting spherical waves, right? It's the light, the electromagnetic waves are dispersing in a spherical way. So they are perfectly spherical, and they are what we call plane waves, right? And when the minute they touch the atmosphere, they become perturbed, as you see in the image, right? When they enter the atmosphere, the waves is no longer perfect, and now becomes perturbed. Now this animation is showing how the laser guide star system works, and this is built particularly to deal with this problem, right? You have a laser which shoots a beam of light at 589 nanometers. And this beam of light, this laser, will interact with atoms at the atmosphere. And you will see how in just a minute. So that's Gemini telescope. And now you will see the laser getting activated and then shooting, right, this beam of light up to the sky. And so this is what happens when people are doing laser guide star observations. So there's that laser, right, dispersing out to space, and it'll reach an altitude of about 90 kilometers. That's where the sodium atom layer is. And so the laser will interact with the sodium atoms, and it's going to excite the atoms. And when the atoms are excited, they emit light. And so we can essentially create a fake star, an artificial star in the sky, any point, anywhere that we want. You just have to point the telescope to the location that you want to observe, and you shoot the laser, and you can create this artificial star. Again, it's completely artificial. It's made by the interaction of the laser with the atoms, right? So once the light, the observation, meaning once the light of the sodium atoms comes back to the telescope, then all that light is collected with the telescope, and it goes through a system of what we call adaptive optics. So that's the light, right, being collimated through the different optics. That you have the beam splitter, and this red light is separated from the blue light, and the red light goes to a computer. In this case, where we see the data, the science data, and you see that the star is fluctuating, right? It's moving because of the seeing, because of the way the atmosphere moves in that animation that we saw before. So that's showing just how perturbed the waves are, right? And now what do we do with the blue light? The red light is used for science, but the blue light is used to give information to the mirror. So with this information, the mirror deforms itself. That's why it's called a deformable mirror. And the mirror deforms in a way that it perfectly cancels the perturbation that is inherent from the atmosphere. And once we cancel that perturbation, we can recover the original wave, the original spherical wave. And so you end up with a perfectly circular point source. So that's the way adaptive optics works. And now let me just talk about stellar clusters. So star clusters, you probably heard of them, and they're very common objects of study in astronomy. We have open clusters and globular clusters. Usually globular clusters are older, and they have, tens of thousands, millions, tens of millions of stars, whereas open clusters are smaller objects. They go from, hundreds to the order of thousands of stars, and they're usually younger as well. And they're great laboratories to study stellar evolution. And what I mean by that is that because of the properties, the physical properties of clusters, the fact that they are all together in the same region of the sky, the fact that they are all born from the same cloud, they are born at the same time, and they evolve, therefore, in a similar way, allows us to study stellar evolution in a very defined framework. That's why they make such great laboratories. And here is an example of an open cluster. This is M25, and this is an example of a global cluster taken with a Hubble Space Telescope. This is Messier 13. So the way that these clusters form is very important, right? Because the fact that they are born from the same cloud, the same molecular cloud. That's the reason why they are so important. So in this animation, you will see how this gas cloud, which is this red circular object, will essentially collapse because of gravitation, and gravitation will make, the gravitational force will make that the cloud collapses into itself, and little clumps will start forming. So you will see what I mean. So as the cloud collapses into itself, clumps of matter start to form, and these clumps become deeper wells of gravitational force. Therefore, more matter falls into these different clumps of matter. And that's how you start compressing all the matter and start forming stars. And now you, at the bottom right, you begin to see many, many stars that are being formed from the gas cloud. So that's how the cluster is forming. As you see, they are all formed from that same filament of the gas cloud. So this is a very, very nice animation showing the way that the cluster forms. That's why we call it a simple stellar population, because they are simply formed from the same cloud and they have the same, roughly the same chemical abundances. So when we take an image of a stellar cluster, a globular cluster in this case, right, showing in this on the left, we can either do photometry or we can do spectroscopy in most of the cases. When you do photometry, you measure the brightness of each star, and that's what the diagram in the right is showing. That's called an HR diagram, or a color magnitude diagram. And when you measure the brightness of each star in different filters, you can construct a diagram like this, right? And you can measure the age, for example, the distance, or the metallicity, the helium abundance for this particular cluster. And when you take an individual star, and that's at the bottom left, we're now looking at an individual star, one star out of the collection of thousands of stars. And you put the light of that single star through a spectroscopy, and you can obtain the spectrum of the star, and that gives you access to the detailed chemical abundances. All those absorption lines that you see in the spectrum are what gives us the information of what chemical abundances are present in this star, and by extension to the entire cluster, because we assume that the cluster has roughly the same chemical abundance. In practice, what you do is you make this observation for many, usually dozens or hundreds of stars in a cluster, and then you can combine all your measurements, take averages, or just study the way that the chemical abundance changes as a function of distance from the center, for example, and things like that. So those are the two main ways that we can study clusters: through photometry, right, by looking at the brightness, or through spectroscopy, by dispersing the light into all the different wavelengths and study the chemical abundances. So that's how we, and because of that, because of the access to that information, we have access to the age, right, to the distance, and to the chemical abundances. We can construct this concept of a stellar population. And so we define a single generation of stars by having a common age, a common chemical composition. Again, this is only approximate. It will never be perfectly equal. And a distinct spatial distribution in space. So they are all located within this circular or spherical distribution, and they have distinct kinematics as well. That means that they're moving together. They're moving. They're all orbiting, say, the center of the galaxy, or whatever system they are in. And of course, in our galaxy, you have hundreds of these stellar populations. So you have several stellar populations living, coexisting in a single galaxy. And for example, in the Milky Way, you have something like 150, close to 200 globular clusters, and many, many more open clusters. So how do we test the stellar evolution? I talked about, I mentioned stellar evolution before, but I didn't explain what it is. So the stellar evolution is just the theory that explains how the star evolves in its life, how it's formed, and how it will evolve, how the brightness of the star and other physical parameters like its size, its radius, how those things will evolve in time. That's the stellar evolution. But the problem, of course, is that all of this, the changes in the star, are in time scales of billions of years. So we cannot sit and wait for 1 billion years and see how the sun changes. There's no way we can do that. So the only way to solve that problem is to observe stars at different ages, of course, and then you collect and you build this comprehensive sequence of evolution. So we can observe many star clusters at a wide ranges of ages. We can study young clusters and old clusters, and then essentially look at the evolution of stars, because we're looking at clusters at different levels of evolution. So each cluster therefore provides a snapshot of stellar evolution at a given level of evolution. Okay, so each cluster is one snapshot of the evolution at a given time. That's very important. And again, this is a diagram showing the color magnitude diagram, or also known as a HR diagram. And the one very important aspect of this diagram is the turnoff point, which is at near the bottom, at the middle, right? There's an arrow showing, and it's labeled as turnoff. That point is where essentially where stars evolve off from the main sequence of their evolution. So they spend most of their time at this main sequence level of evolution, and at some point they become old enough that they evolve away from this point, and that's the turnoff point. That's the point where the stars begin evolving off and away onto the red giant branch, the horizontal branch, the asymptotic giant branch, and so on. So the turnoff is a very important point, because we can use the structure of this diagram, the structure of these points, and in particular, we use the location of the turnoff to estimate the age of globular clusters, and thus of the galaxy, of course, because the older the clusters, that means that the older is the galaxy, right? Because the galaxy, the clusters were formed in the galaxy. So to measure specifically to have a number, to have a number for the age, we use models, and the models that we use allow us to draw these lines that you see here. This is the same HR diagram, the same color magnitude diagram that you were seeing before, but now we are zoomed in a region around the turnoff. Okay, so it's the same region. If you remember you remember where the turnoff was. Now we're zooming into the turnoff, and now we can draw these lines, and these lines are called isochrones, meaning that they are all of the same age. So each line corresponds to a different age. And so it's as simple as trying to fit the isochron, trying to look for the best fit model. So which isochron fits your observations the best? So which age? So essentially what you're doing is finding the best age that explains the observations. And of course, in practice, this is way more complicated than just trying to fit a curve. But this is I guess a simple way of explaining it. So when you do that, you can study and you can measure the ages of your clusters, right? By using isochrones, using your stellar models. In this example, I think this cluster in particular had an age of about 12.3 billion years, or giga years. That's what GYR stands for. So when you measure the age of many clusters, you can begin to understand the formation of the Milky Way, okay? So in this diagram, let's just focus on the left diagram for now, okay? So just forget about the right diagram, which is essentially the same information. So just look on the left, and you have age in the vertical axis, and you have metallicity on the horizontal axis. So yeah, don't pay much attention to the metallicity for now. Just focus on age. Okay, so the blue clusters, each point is an individual cluster. Okay, so the blue clusters which are at the top, that means that they're very old. It means that their age is high, is about 13.5, right? 13.7, close to the age of the universe. So it happens that the blue clusters are the ones that are in the inner halo of the galaxy. And it happens that the red clusters, the ones that are color red, are in the outer part of our galaxy. So that's very interesting. We see that the blue clusters, right, the ones that are in the inner regions, are older than many of the clusters in the outer regions. So this is a way that we can build some idea of the way that the Milky Way forms. So we believe that diagrams like this are suggesting that the inner halo formed initially with rapid assembly. So it formed fast at the beginning of the history of the Milky Way. And the outer halo, right, the red clusters, those were possibly accreted from other galaxies, right? Or galaxies that were orbiting our Milky Way, and they had lower mass. So because they had lower mass, they were accreted. Our galaxy was able to accrete these galaxies and therefore accrete the clusters that were located in these dwarf galaxies. So they are orbiting now at a further distance from the center of the galaxy, and that's what we define as the outer halo and the inner halo. So with diagrams like this, we can get some idea and understand the way that the Milky Way forms. And so the message that this is sending is that the Milky Way formed fast and formed the inner halo very fast with a rapid and self-enrichment type of way. And then it accreted stars from dwarf galaxies that were orbiting our galaxy. And that's how the outer halo was formed, right, in a very simplistic way. So now let's look at a globular cluster, and you see that the density of the clusters obviously changes, right, as a function of the radial position. So the further away you are, the density is lower. In this case, you have about 0.5 stars per cubic parsec, but as you move to the center, the density can increase to near 100 stars per cubic parsec. So the inner regions of globular clusters are very, very dense regions. So it's very hard to observe these regions because you have so many stars that it's almost impossible to resolve each individual star because of the high density. And just to give you an example, on the left, you have an image of an entire globular cluster. And you see that there is right this image overlaid right at the center of the cluster, and that's actually an image taken with Hubble. So that's just so you can see the different sizes of each telescope, right? To put it in some way. So with a ground-based telescope, we can observe a larger portion of the sky and we take the image of the full cluster, but then we go to space, we use Hubble, and then we're observing only that tiny, we're observing only the tiny area of the inner region of the cluster. That's what Hubble is doing, is only observing the small area at the center. And then when you look at the picture, is of course the diagram on the right, that's the image taken by Hubble. And now look at the amount of stars that Hubble can resolve, and that's only at the center, right? So it's very hard to do these observations, and only Hubble, or not too long ago, Hubble was the only telescope that was able to do these kinds of observations for optical wavelengths and or near infrared wavelengths. But we have a way of getting close to this from the ground, so we don't have to go to space anymore. We can actually do this from the ground, and that's when adaptive optics comes into play. So you already saw the animation, right? That you shoot this laser, you create this artificial star, and that's how you can calibrate for the perturbations of the atmosphere. So we have three types of AO that I'm showing here. We have classical AO. AO means adaptive optics, of course. You have the tomography type of AO, and you have the multi-conjugate adaptive optics. So in classical AO, you only have one deformable mirror. You have one guide star. And then you have your science target, which is the galaxy, right, shown in blue. For the tomography type of AO, you still have one deformable mirror, but you have more stars, more guide stars. So now the fact that they are spread out around the object that you want to study means that you can correct for the perturbations of the atmosphere at a larger scale, okay, at a larger spatial scale. But now when you want to do that at different layers of the atmosphere, you need more deformable mirrors. And that's how we construct multi-conjugate adaptive optics. So you have many deformable mirrors, not only one, but several, and you use many laser guide stars. And doing that, we can obtain corrected images on a much, much broader region of the sky. So we can observe a large portion of the sky and correct the seeing at at all this high, large spatial scale. So in the case of Gemini South, the laser guide star system at Gemini South, that's the laser that you observed, that you saw in the animation. This laser will create 5 stars, 5 laser guide stars in the sky. And that's shown right there, right? Those are the laser guide stars. So it's not 1, it's actually 5 stars. So once you do that, the telescope will collect the light of the artificial guide stars, not only of the artificial guide stars, but of the science target that you want to observe itself as well. All of that light goes into the instrument. And this complicated array of optics, that's how the instrument works, right? I'm not going to explain because it will take forever, but there are many, many mirrors and different optical elements in the instrument. So it's a very complicated array of optical elements. But eventually, once you have the wavefront that has been corrected by the deformable mirrors, as you saw in the animation, then the corrected light will go into your science instrument, right? So that's the path that the entire light goes through. It's collected by the mirror, by the telescope. It goes into your adaptive optics system, and then the system, outputs the corrected light, which goes into the instrument. And in this case, the instrument is called GSAOI, and that's the detector, and that's an image that you see here, a large image taken with GSAOI with the detector at Gemini. And at the right, you have 3 different panels. That's just the comparison of what you can observe for example, seeing limited at the bottom, which means no AO. And then you have classical AO and you have GEMS, right, which is the multi-conjugate AO. And as you see, this is actually very comparable to HST. So on the left, you have the same image, but taken with HST. On the right is the image taken with Gemini and its multi-conjugate AO. So now we are approaching the type of resolution that we can obtain with Gemini. So we can do this from the ground, right, using adaptive optics. So the point of this is that we can now use this and study the dense cores of globular clusters. So in the near infrared, it's very important to obtain this color magnitude diagram, as I was explaining earlier. So these are the isochrones now in the near infrared. And when you plot many isochrones for each isochrone corresponding to a different age, right? So you have 8 gigayear or 10 or 12 or 14. You see that the form, the shape of the isochrone changes. But there's one point that doesn't change. That is the low May sequence downturn, right? Is the red star at the bottom near the center right. That location doesn't change. So we can use that information and plot now the isochrones and overlay the isochrones on top of the data. And because the downturn doesn't change, what changes only is the turnoff. So that's how we anchor the model, or that's how we know where the model is supposed to be, right? That's essentially the idea behind this technique. We know where the model is supposed to be because that location doesn't change. And the only thing that changes is the turnoff. So we can obtain very precise ages once we fit the curve as I was explaining earlier. And so we're doing that with Gemini. We're doing that for many, many clusters. In this case, you have NGC 3201 on the left and a different cluster on the right. And for each of those, we obtain a very precise age. And so that's our survey. That's the project that we're doing. It's called the GEMS JSAOI Global Cluster Survey, or G4CS for short. And so we're studying about 18 nearby global clusters using this technique, using the laser guide star system at Gemini South. And our goal is to obtain very precise ages. Okay, and once we have these very precise ages, we can understand the way that the galaxy formed. So I think I'll end now with these conclusions, just to summarize what we talked about, right? Astronomical observations are not simple. I think now you have a very good idea, a very good understanding how complex these observations are. We have many problems. You have the background coming from the atmosphere, you have the atmosphere, turbulence, the seeing, and all of that. And the global clusters themselves are very problematic because they're very dense. But when you combine these technologies like adaptive optics, you're able to actually study and obtain images of these clusters. Okay, I'll end up here. Thank you for your attention. I hope this was entertaining, and I'll be answering questions now.
Thank you so much for this amazing meeting. It is a very deep topic. We enjoyed every minute of it. If you have any question, you can ask by raising hand or by writing them in the chat box. Thank you.
Okay, thank you, Celine. As Celine mentioned, you can either buy video or I can give you access. You can type it or I can give you access to ask personally. Dr. Mirko, and I personally, I have a question. I'd like to ask to kick things off.
Yes.
We all saw the launch of the James Webb Telescope. I want to ask you, how does the launch of the James Webb Telescope will affect your field and what you just talked about today in general? Like, we know that the James Webb is the successor or replacement of the Hubble Telescope. You talked about the Hubble Telescope. Obviously, the James Webb Telescope will give clearer images, farther images. How will this affect this in general, what you talked about today?
So it will be a great improvement over what Hubble can do. Not only is the size of the mirror larger now, the James Webb telescope actually was built specifically to look into the near infrared. It was optimized for the near infrared. And that's why when you see images of James Webb, you see that the mirror, it looks golden, right? Because it is in fact covered with gold. It's coated with a thin layer of gold atoms in the mirrors. And the reason NASA did that is because gold is very reflective in the near infrared. So they are optimizing the reflectivity of the telescope, of the whole telescope, particularly for near infrared radiation. And well, the reason that they want to optimize the near infrared radiation is because now we're at a point where we can study exoplanets with very great detail. And when you want to study exoplanets, then you want to look in the near infrared in particular. That's the type of radiation that is most important, that can give you the most amount of information when you want to study the atmosphere of the exoplanets. So it will be optimized for near infrared. It can also observe in the optical as well, of course. And for fields like globular clusters, what we were talking, it will be definitely a game changer. We will have images that are, I could not say how many times more the resolution will enhance. I don't have the number in my head, but the resolution will be, several times larger compared to Hubble. So we can resolve now the dense cores of clusters at much higher detail. So it will definitely be game changer for the field of stellar astrophysics and globular clusters.
Thank you so much. It's a personal question. We have some questions we received from Instagram in general, from our clubs. The first question is, what is the furthest object we can see with your telescope?
The first object?
The furthest.
Well, that would, oh, the furthest, okay.
Yeah.
So as I tried to explain at the beginning of the talk, it all depends on how long you take the exposure. A 1 second exposure is very different from a 10-hour exposure. But when you have 8-meter class telescopes like we have here at Hawaii, usually our exposures will be of the order of 20 minutes or maybe at the most 30 minutes probably, because there is a limitation. You cannot take images for longer time than, say, 30 minutes. The reason is because you have cosmic rays, right, colliding to the detector. So if you spend a whole hour with your aperture open and collecting light for a whole hour, you're going to end up with so many cosmic rays that all you're going to see is cosmic rays, right, which is essentially garbage. It's trash. We don't care about the cosmic rays hitting your detector. So you have to keep your exposures at most 20 minutes or 30 minutes so that you're not saturated by cosmic rays. So when you have that in mind, you take a 20-minute exposure with your 8-meter class. You can easily go to redshift of 6 or 7 or 8 in space, and an object that is at redshift 6 or 7 means that it's only probably a few million years after the Big Bang. So you can go as far as a few million years after the Big Bang. That's how far you can go with an 8-meter class telescope. But you have to take a long integration again.
Okay, thank you very much. We have another question also from the chat on Insta. Sorry, not the chat. We have a poll on Insta. Why is it important to study globular clusters?
So, like I was trying to explain earlier, let me see if I can go back to some of these slides. Yeah, okay, so this bullet point here gives some understanding of that. So the globular clusters are really important. So trying to explain, they serve as laboratories for stellar evolution, but more importantly, they are a type of fossils of galactic formation. So they are fossils in the sense that they are a relic of the past. They are a relic of how stars formed billions of years ago. Okay, when you look at a globular cluster, you're looking at stars that were formed billions of years ago at the early stages of the Milky Way. And so you can derive things like, for example, the lower limit of the age of the Milky Way, right? Because if a cluster is 14 giga-years old, that means that the Milky Way has to be at least 14 giga-years old. And also you can understand the formation process of the galaxy. That's another reason why globular clusters are important. For example, I think it was in the 60s that a famous astronomer named as the name of Shapley, he studied the distribution of the globular clusters in the sky. So by looking at how many clusters in each region of the sky, he was able to form to understand the shape of the galaxy, right? So the very first astronomer that understood the shape of the galaxy was this astronomer looking at the location of globular clusters, right? Because they're bright, they're easy to distinguish in the sky. And so you can essentially build a map of the galaxy just by locating the clusters in the sky. So those are some of the applications, the scientific applications that you can do with globular clusters. But the most important one and the one to keep in mind is that they really serve as fossils of galactic formation. They are the best way that we can study stellar evolution. I hope that's clear.
Okay, thank you very much. We have another question from the Zoom chat. Is it possible for some globular clusters to be older than our galaxy?
That's a great question. That's really, it's going into semantics at this point. So imagine we have two galaxies at 13.5 gigayears ago, so near the age of the universe. Imagine we have two galaxies at about the same mass, and they are together, and essentially eventually one of those galaxies will become slightly more massive than the other, and it will accrete this other galaxy, right? And so both of those galaxies will merge into a single galaxy. Now that could have been the case of the Milky Way, and but once they merge, you call the end result, you just call it the galaxy, right? That's just the Milky Way. But imagine that the star that we are, right, our solar system, imagine that our solar system was in the lower mass galaxy, the one that got accreted into the other one. So if that was the case, that means that we come from an accreted galaxy instead of the one that was the accretor. So that's what I mean when I say it's maybe semantics, because it depends how you define what galaxy we were formed. Our sun was formed in. So if that was the case, then I guess yes, some of the clusters from the other galaxy were older than our galaxy, if our galaxy formed at a slightly later time than the other galaxy. But that's just being way too detailed. But in general terms, globular clusters can only be as old as the galaxy. That's the general understanding. And but if you want to look at a very precise and particular case, you can make the argument that maybe some clusters were formed in a older galaxy that formed slightly earlier in time. But no, usually each cluster will be as old as the galaxy.
Oh, that's so basically it's semantics, as you said.
Yeah, yes.
We have a question from Ahmed Jabakanji in the chat. There's a new study that refers to existence of a swarm of black holes at the center of globular clusters. Is there any possible expectation of capturing collisions?
Well, yes, we capture those collisions with gravitational waves. We have detectors of gravitational waves. They're called LIGO, and
yes,
and
LIGO.
I forgot the name of the other detector. But these detectors are especially built to measure variations in the gravitational field. And so once the gravitational wave comes, these detectors will slightly get perturbed, and that small perturbation is recorded by the instruments. And that's how we detect when an event such as the collision of two black holes can occur in the nearby vicinity. And it has happened, right? It happened for the first time only a few years ago, and it's continuing to happen. We are continuing to detect these events. So if we have two black holes that are massive enough to emit gravitational waves that are strong enough, then we will measure them with our instruments at LIGO. That's a completely different type of astronomy that I didn't discuss here.
Great. So we should have believed Einstein when he theorized the gravitational waves before. Okay, listen,
for sure.
We shouldn't wait for this long
yes,
to believe him.
For sure.
We have a question from Ali Johnson. You're free to talk, Ali. I gave you access. You're still muted, Ali. If you can unmute yourself, please. I gave you access if you can unmute yourself. Try to unmute now. Or now, for example, try please. Technical difficulties, sorry. Is there any, I'll see if there's any more questions until Ali figures out how to unmute himself. This is actually a bit of a sophisticated question, might I say. How reliable is it to use globular cluster luminosity function as distance indicator? The person who said this must have experience with them.
As distance, can you repeat the question, please?
How reliable is it to use globular cluster luminosity function as a distance indicator?
Okay, it's a completely reliable. I mean, it's one of the methods that we have. In particular, what you do is the luminosity profile of a cluster basically means how many stars are in the cluster at a given brightness, or yeah, essentially that. So when you measure the tip of the red giant branch, or the brightest stars in a cluster, they are in the asymptotic giant branch, and the tip of that branch, the brightest point of the diagram, of the color magnitude diagram, gives you a measure of the distance. Okay, because that location of the tip of the giant branch, it's described by theory very precisely. So we know, because of theory, how bright those stars will be. And so because we know how bright they should be, then when you look at them and you see how bright we observe them, then you can infer how far they are in distance. So it's one of the methods that people use to measure distances, and it's done all the time. I mean, in particular, when you have clusters that are very unresolved, then they are all mixed together and you cannot really distinguish individual stars, but you can kind of get the brightness of some of the stars. And then one good method to derive the distance is doing that. It's exactly that. It's looking at the brightest star that you have, then you define that as the tip of the giant branch, and then you calibrate the distance in your models, and you find what's the best distance that explains that. For example, that was done for clusters that were observed only recently, years ago, in a galaxy that is lacking dark matter. You might have read in the news, it was very, very controversial. It was, seen in many scientific news outlets, and the authors believe that they have found a galaxy that was lacking dark matter, and the way that they arrived to that conclusion was by measuring the distances to the clusters in the galaxy, and they actually used that very same method, the tip of the RGB. So yeah, it's a perfectly reliable method, but you have to know what are their limitations, right? Other methods are much more reliable, like when you use variable stars, and Mo is an expert in that field. When you use variable stars, you can really measure the distance with much better precision.
Okay, thank you very much, Dr. Mirko. Let's see if, okay. Ali, do you want to say something before we end? Is it, if no, we'll end it now. Okay.
No, I guess it worked, I guess. Sorry for the technical difficulty. It appears the Zoom quite complex for me. Okay, back to the question. I wanted to ask if are the distribution of globular cluster systems in giant elliptical galaxies spherical?
So again, you're asking about elliptical galaxies. What exactly is your question?
The distribution of globular cluster systems in a giant.
Oh, okay.
Yes.
So you want to know about the distribution of clusters in elliptical galaxies?
Yes, and if they are spherical.
Yes. Okay. So yeah, great question. I didn't mention at all that there are essentially two major types of galaxies. We have, elliptical galaxies and you have spiral galaxies. Of course, you also have irregulars, but usually people study spiral galaxies or elliptical galaxies. And the way that the stars are distributed in each of those galaxies is very, very different. So in an elliptical galaxy, you will have a very, very, very extended halo. And the globular clusters are located in this extended halo distributed spherically in this galaxy, right? That's where they're called elliptical, right? It's really an ellipse. Whereas on a spiral galaxy, you have most of the open clusters actually live in the disk of the galaxy, and the globular clusters also live in the halo, which is also spherical. But elliptical galaxies are much, much larger than spiral galaxies. So the distribution in a spherical galaxy will be spherical. They are spherically distributed around the galaxy, but you can find them very, very far out in this halo. So very away from the elliptical, from the main part of the galaxy, you will find many clusters distributed spherically. I don't know if that's exactly what you meant, but yeah, you can ask more if you need to.
Oh, I guess I understood. Thank you.
Okay, thank you very much, Ali, for your question. And thank you for everyone who joined us tonight, and for Mo and all of the clubs who joined. And especially the biggest thank you is for you, Dr. Mirko, for this, honestly speaking, it answered a lot of questions I had in mind. And this little bug that always followed me wherever I study about galaxies and whatnot. So thank you very much for being with us, and thank you for everybody who joined us tonight. We hope you can join us in the next talk we have, and we're working on more things for you. Thank you, everybody, and good night.
Thank you to the organizers. Bye-bye.
Bye.